Welcome. Today, we are diving headfirst into a classic, a real rite of passage from a book that has challenged physics students for generations, i.e. Irodov's Problems in General Physics. We're going to completely dissect and conquer problem 1.29, all about projectile motion. Let's do this.
But before we even start, let's take a look at a fantastic piece of advice from Irodov himself. He tells us to solve problems in the general form, using variables, not plugging in numbers right away. This is such a powerful way to think because it shows you the real physics behind the answer, and that's exactly how we're going to approach this today.
Okay, here it is, the problem itself. A body is thrown with some initial speed, v0, at an angle alpha. We have to find, well, basically everything. The total time it's in the air, how high it goes, how far it goes, the actual equation of its path, and then, the tricky part, the radius of curvature at the beginning and at the very top. I know, it sounds like a ton, but trust me, we're going to walk through it step by step.
So, here's our game plan. We'll start with the single most important idea, how to deconstruct the motion. Then, we'll use that to find the time, height, and range. After that, we'll figure out the equation for the path itself, tackle its curvature, and finally, we'll put it all together. Sound good? Let's get into it.
So let's talk about deconstructing projectile motion. This is the foundational principle. When you're staring at an object flying in this nice two-dimensional arc, the big question is always, what's the first step? Well, the entire key, is unlocked by one beautiful, simple principle.
Right? It feels complicated. You've got this forward motion, you've got this upward motion, and the whole time, gravity is pulling it down. It's a lot to juggle at once, but there's an incredibly elegant way to simplify the whole thing.
And here it is. This is the secret sauce. This is the big idea that makes everything else possible. We split the motion into two totally separate, independent problems. Horizontally, along the x-axis, there's zero acceleration. The velocity is just constant. Simple. Vertically, along the y-axis, it's just an object being thrown up and falling back down with a constant acceleration g. That's it. One complex problem just became two much simpler ones. This is our entire strategy. Okay, section 2. Time, height, and range. We're going to solve the first two parts of the problem right now. Let's put that awesome deconstruction principle we just talked about into practice.
First up, how long is this object actually flying through the air? Now to figure this out, here's the really cool part. We can completely ignore the horizontal motion. Just pretend it doesn't exist for a moment. The total time of flight is decided only by what's happening in the vertical direction.
The logic here is just beautiful. The object starts on the ground, goes up, and lands back on the ground. And because that path is perfectly symmetric, the time it takes to get to the very top is exactly half the total time. Now, what's the magic insight at that peak? Well, for just one split second, it stops going up and hasn't started going down, so its vertical velocity is zero. We can use that fact in our kinematic equations to solve for the time to the peak, which turns out to be v0 sine alpha over g. To get the total time, we just double it. Easy as that.
Now that we have the time, everything else starts to fall into place. To get the maximum height, we again focus only on that vertical motion, using that same trick. Vertical velocity is zero at the top. And for the horizontal range? Now we switch over to our other simple problem. The range is just that constant horizontal speed multiplied by the total time it was in the air. See how breaking it down just makes it all click?
And after we do the algebra, here are the beautiful results. Notice how both of them depend on the initial velocity squared? That means if you launch it twice as fast, it goes 4 times as high and 4 times as far. We've got our clean, general formulas, just like Irodov told us to get.
Now for a fun little bonus question from the book. It asks, at what angle are the height and the range exactly the same? Well, to figure that out, you just set our two new formulas equal to each other. You do a little bit of algebra and trig, and you find it happens when the tangent of the angle is exactly 4. That works out to be about 76 degrees. Pretty neat.
All right, next section. Let's find the equation of the path. This time, we're not just looking for how far or how high it goes. We want to describe the exact shape of that arc. We want to find y as a function of x. So the strategy here is a classic move in physics. We've got one equation for our x position over time and another one for our y position over time. But we want to connect y directly to x, right? So what's in the way? The time variable, t. We have to eliminate it. The easiest way is to use that super simple x equation to solve for t. Then you just take that expression and plug it right into the y equation. What you're left with is the equation of the path.
Okay, we've arrived at the final and maybe the most advanced part of the problem, finding the radius of curvature. So what does that mean? It's basically a measure of exactly how sharply the path is bending at two specific points, right at the beginning and at the very peak of its flight.
So what even is a radius of curvature? Well, imagine trying to fit a circle that perfectly matches the curve at one single point. The radius of that circle is the radius of curvature. Now, the formula for it is speed squared divided by something called the normal acceleration. All normal acceleration means is the part of the acceleration that is perpendicular to the velocity at that exact instant. Think of it this way. Only acceleration that's perpendicular to your motion can actually turn you. Any acceleration parallel just speeds you up or slows you down. So AN is the turning acceleration.
So all we have to do is apply this formula at our two moments. Right at the beginning, the speed is v0, and the part of gravity's acceleration that's doing the turning is g times the cosine of alpha. But at the peak, things are different. The speed is slowed down to just its horizontal component, v0 cosine alpha. And at that exact moment, gravity is pulling straight down, which is entirely perpendicular to the motion. So we plug these different values into our formula, and we get our two different radii of curvature.
And with that, we've done it. We've solved every single part of this Irodov problem. So let's bring it all together and take a look at the complete picture.
And here it all is, the complete solution set for problem 1.29. We've got the time of motion, the max height, the horizontal range, the parabolic equation for the path, and the curvature at the start and the peak. The whole shebang. A complete description of the motion, all derived from first principles.
But look, these formulas are great, but they are not the real prize here. The most important thing to take away from this is the strategy. That idea of taking a big, complicated, two-dimensional problem and deconstructing it into two simple one-dimensional problems, that is one of the most powerful tools in all of physics. You can apply it almost everywhere.
So we have absolutely mastered the ideal case. But remember, our entire solution was built on one crucial assumption, that we could ignore air drag. So that leaves us with one final, very important question to think about. What happens in the real world when we can't ignore it? How does that change everything we just derived? Thanks for joining me for this breakdown.